So I will start out ranting because I can. If you don't want to be here today, I'm not using iClickers, just leave. So I had like 3 students who were literally just looking at their phone the entire last section, and I didn't say anything, but it was clearly irritated. So today I'm trying to go through all the Excel stuff to give you all the tools you need for that 4th Excel, so you can, do it almost all the points. Right? So all we're going to do is Excel today. We're going to use this 2 population hypothesis testing blank file that we kind of already started working on. But we're going to look at when we take the difference between sample proportions, and we're also going to look at situations where we have sample means, but we only have sample variances. Okay. So the first one we'll start out with our sample proportions. Right. Also, just to kind of mention, I put that 4th Excel homework up there. So it's going to be very, very similar to, what we do today, right? Those first 2 problems. We probably won't get to the 3rd problem until Monday, just because I want to be a little more deliberate in what we're doing today. And I'll kind of even pull this up later to show you kind of some similarities, okay? So we're going to start out. One thing I didn't have in here is sample proportion and sample size, right? So I'm going to be comparing, I've got these 2 different samples of males and females, and we're eventually going to compare their BMIs, but maybe we're considered we want to make sure these samples have similar demographics, right? So I've got this variable, which is a 1-0 variable, which is white if the individual is white, 0 if they're non-white, right? So I'm going to try to calculate 2 sample proportions and then 2 sample sizes, right? One from my male group, one from my female group. So I'm on this female data. I'll use my average function, right? And actually, I'll zoom in a little bit here so we can actually see what I'm doing. So remember, we said the sample proportion is just a unique case of the sample mean. It's when we find the mean or the average of this 1-0 variable. So Control Shift, Command Shift on a Mac, hit the down arrow, hit Enter. All right. I then going to use this count function, go up here, I'm going to select, start in this first cell, Control Shift, Command Shift on a Mac, hit the down arrow. I've now got my sample proportion and my sample size for this female group, right? I think I'll end up defining this as kind of group 2. I then go over here to my male data worksheet, and I'm going to have to scroll down a little bit. Right? So I've got this kind of set up to where I've got kind of my male and my female sample proportion, sample size. So I need to now find the average or the sample proportion of my males that are white versus non-white. So I'll go up to the top, select that variable, hit Enter. I've got my sample proportion for males that are white. I'll then use that, count function again, go up here, select that 1-0 variable, hit Enter, right? So I've now got my sample proportion and my sample size, right, for my male kind of sample. I want to put the sample proportion and sample size for the females on the same sheet. So I want it all to be in the same place. So I'm going to start with an equal sign and then going to go over to my female data sheet. When I select it, it puts that reference in there for me. And here is where my sample proportion for my females was. Right? That way I'm just kind of like transferring that data over. I'm just cross-referencing across those sheets. I'll hit Enter. Now I've set it up kind of nice so that if I copy this down, notice it updates my cell reference on that worksheet to be the next lowest value. So I don't have to kind of go through that process for every single statistic if I kind of set that up, in the same way on both sheets. Okay. Any questions up at this point? Nothing too crazy. We've done all this stuff before, right? We're just finding the sample sizes. I'm then going to come down here. So I've got my confidence interval equation. We said, look, it's really just a matter of using Excel to be our calculator, right? We've got everything we need. The sample proportions, the sample sizes. The only thing left we need to do is find this z-value in Excel. Okay? So anytime I'm starting with the area that I want in the tail. So remember, what we're doing is we're trying to find the number of standard deviations away we need to go to get alpha total outside of my confidence interval, right? So I want to know what's that z-value that gives me alpha over 2 on each side, okay? So if I know the area I want in the tail, and I want Excel to tell me that number of standard deviations, does anybody remember what function can we use there? So first of all, what distribution are we using? Yeah, so I'm going to start out with norm.s, right? Standard normal. Now I have one of two things. Maybe I thought it was that norm.s.dist function, but it even reminds me, oh no, that's when you know the z value and you want Excel to give you the area in the tail. Here, we know what our alpha values are. So this first one, I've got what, an alpha of 0.1. So I'm going to know the area in the tail. I want Excel to give me that z value. So instead of norm.s.dist, I should use what? Yeah, I and v, right? The area I want on each side is alpha divided by 2. I'm going to have one small problem with this, right? When I hit enter, right, I get negative 1.65-ish. But that positive and negative are already built into that lower and upper bound equation. So what's the thing we said that we can do to kind of get rid of that negative sign? Yeah, just the absolute value, right? And it'll yell at me because I didn't close the other parenthesis, but it'll do it for me if I hit enter. Okay. Now I copy this down. It updates my alpha for these different levels of confidence. And I've now very quickly got that z value for 3 different confidence levels that would give me half of alpha. Sorry. Yeah, half of alpha on each side of my confidence. From here, it's just using Excel to be a calculator. Okay. So for my lower bound, I'm going to define this as male, the proportion of males who are white minus the proportion of females who are white in these data sets. Okay. So I just take that sample difference, or the difference in my sample proportions. I'm then going to subtract my margin of error. Well, what's my margin of error? It's the number of standard deviations away I want to go, multiplied by, remember, what does this kind of represent? The standard deviation of my sample statistic, or here, the standard deviation of the difference in my sample proportions. So, square root of this group's sample proportion times 1 minus that group's sample proportion divided by that group's sample size. Now, I could have calculated like this entire thing in a different cell if that makes it easier. I'm just going to type it all in at once here. I'm then going to add to that, right, the second group's sample proportion times 1 minus that group's sample proportion divided by that group's sample size. So all I'm doing here is using Excel to be my calculator. Okay. Questions on that? It's gonna be too crazy. So it's just really similar to what we did with one population example. It's just there's a few more moving parts. Okay. So if I copy this down, what's the only thing that should change at different levels of confidence? My z value, right? So everything else I want to do what to? So here's my reference for the z value. That's the only thing I don't want to freeze. So I'm going to select, select this. F4 or FN F4 if you have an FN key. Command T on a Mac if you don't have an FN key. Select all of this. Same kind of thing. Now everything hopefully should be good to go when I copy this down. The only thing that will update is that z value. Now, because I'm in this cell, I'm just going to do this right now just to save some time. If I've got all of this, what's true about this equation? For my lower bound, what's the only thing that changes if I want to get my upper bound? Add that margin of error. So I'm going to select that entire equation. So how I did that real quick, if you just like triple click, right? So the first click, there you go. I'll highlight the whole thing. You could highlight it with your mouse if you want to. I'm going to use the shortcuts so you can't see what I'm doing, but I'm copying, hitting enter to get out of the cell, pasting. It should give me the exact same value. But remember for my, I don't know why I put UP, upper bound, right? So it should be everything is the exact same except for instead of subtracting my margin of error, I'm going to add that margin of error. Okay. Now I've got my upper and my lower bound. Okay. I'm then going to highlight these two. I can copy them down, and I've got my upper and lower bound pretty quickly. Okay. Any questions on that? You want to see one of those cells again? Okay with this? There's not a whole lot of us here today, so now's the time to ask questions. Make sure you're getting all your questions answered. Right? Okay. So the next step, we've got these confidence intervals. I'll try to make the connection here in a second. But let's say instead we want to do some hypothesis testing. And I didn't type this out, so I'm going to put my null alternative here. So let's say I wanted to assume that, I want to test for whether or not that difference is greater than 0. I'll assume the opposite is true, which is that it's less than or equal to 0, right? So this is my hypothesis test. Right? This is what I want to try to find. What type of tailed test do I have? Yeah, greater than sign, my alternative hypothesis, right-tailed test. Okay. So I'm going to go over here, and I'm going to try to find my test statistic, and then using that test statistic, look up my p-value. Right. So I'm just going to draw this on the board so we have kind of a visual to go along with what we're doing in Excel here. So I wish there was an easier way to do this in Excel. I wish there was like a pre-programmed thing. We'll kind of see. For some of this stuff, there is some stuff that's a little pre-programmed can kind of help us, but for proportions, we're just going to have to use Excel to be our calculator. Now, one of the issues is here, I need to find this P bar first. So I'm going to go up here, right? And I'm going to figure out what this weighted average is between my two sample proportions, right? That's all P bar really is saying. So I'll take my first group's sample size times that group's sample proportion. I'll add to that the second group's sample size times that group's sample proportion, and then divide by the sum of each group's sample size. Right? All I'm doing is using Excel to my calculator. Now, what's one issue I'm going to have if I hit enter here? What did I do wrong? Put the last one in parentheses. I didn't put anything in parentheses, right? So it's going to do the division first. So it's going to divide, it's going to do this first and then start adding things. So I need to make sure that I've got my numerator here in parentheses. Oops. And I also have my denominator in parentheses, right? That way, making sure the order of operations is working correctly here. Okay? So order of operations still matters in Excel. So we need to make sure that we're kind of keeping a close eye on that. Okay. So I've now got this weighted average between these two sample proportions, right? So now it's just a matter of using Excel to be our calculator. We want to find that difference in sample proportions. So that was just my male group minus my female group. Whoops. I'm not going to subtract my assumed true difference here because I'm using an assumed true difference of 0. So it doesn't really matter. So, and that's going to be true for your Excel assignment as well. I'm giving you the assumed true differences of 0. I'm then going to take the square root of that weighted average P bar times 1 minus that weighted average of P bar, and then multiply that by 1 over each group's sample size, right? So 1 divided by group 1 sample size plus 1 divided by group 2 sample size. Okay. All I'm doing is using Excel to be my calculator. Okay. In fact, give me 1 second here. If you're ever having issues with that, sometimes I forget to make it even larger. So this will probably help, right? To be able to see this a little bit easier. Right? So all I'm using is Excel in my calculator. Okay. Now I found a positive sample difference. So notice if I've got an assumed true difference of 0, remember this denominator represents a standard deviation. Okay? Standard deviations are always positive. So the sample difference I find, the sign of that sample difference, in this case it was positive, should always tell me the sign of my test statistic. Sure enough, I get a positive test statistic. Now, we may not be super familiar yet, but if I've got a test statistic or a z statistic of 0.3, my p-value for a right-tailed test is the area to the right of it, right? The probability I saw something as many standard deviations away from the assumed true difference or anything even further, right? The reason why I say any further is because for left-tailed tests, that's actually lower values, right? Going down into the left tail. So at 0.3, what do you think is going to be true about that p-value? it's going to be relatively. So I think about eventually what I want to do. I want to compare this p-value to alpha. So hopefully we're getting somewhat familiar with some of these values. My critical values, if I look at any tail test or any situation, are always greater than 1, right? They're like, I think the lowest it ever gets is 1.28 or something like that, right? So if I've got a test statistic of 0.3, the area to the right of that is going to be relatively large, right? So kind of going into this, I'm already thinking like, I'm probably going to be failing to reject the null here, but we'll work through the process. So if I want to find that area in the tail, we said this earlier, what function would I actually use? I know the z value. I want the area in the tail. Yeah, norm dot, and be careful, not norm dot dist, norm dot s dot dist. We're working with a standard normal distribution. I know the z value, comma, we always use the cumulative option. Only problem is using that cumulative option, it always gives us the area to the left. For a right-tailed test, the probability or the area we wanted was the area to the right, so we need to do what? Yeah, 1 minus that, right? So I just go to the very front. I could do it in 2 cells if I wanted, or I can just put the 1 minus in the front. So I'll hit enter here, and I get a p-value of 0.37. Is that going to be less than any of my alphas? Not even close, right? So I failed to reject at every single level, right? Even though I found sample evidence that the proportion of my male sample, or the proportion of my male sample that was white is a little bit higher, it's not, you know, that difference between those two groups, males and females, wasn't very far away from that assumed true difference of 0. So it wasn't very far away, so why would I be rejecting it, right? It's very possible that if the true difference was 0, that I would see something that was 0.3 standard deviations away from that. Any questions on that before we keep moving? You want to see a cell again, or yeah? This one? Yep. Yeah, so I'll be honest, a lot of this is, you know, being careful with your parentheses when you're typing in these test statistics. Okay. So what if instead of the p-value approach, I wanted to use the critical value approach? So for a right-tailed test, my critical value should always be what? Yeah, it's a cutoff number of standard deviations away. My standard normal or my student t is centered around 0. So a right-tailed test, my critical value should always be positive. And it's going to be the number of standard deviations away I need to go to get alpha total in that tail. So if my alpha, let's say I want to do a 95% confidence or a test, all right? Or if, you know, I want my alpha to be 0.05. Okay. So I'm going to go, oops, what did I do here? There we go. I'm going to go, I know that area I want in the tail is 0.05. I want to figure out the z value. So very similar to confidence intervals, we're kind of using that inverse process. We know that probability we want. We know the area in the tail. We want Excel to spit out at us the z value. Now, the problem is if I just simply tell it alpha, right? What's wrong with this critical value? What did we just say? It's got to be positive, right? Now, that's okay because I've got a symmetric distribution. The area to the right of this critical value will be the same as the area to the left of that negative value. So I could just use the absolute value function and just get rid of that negative sign because I remember it's a right-tailed test. Or if when I tell that norm.s.i and v the probability, that's always the probability in the left tail. So if I want 0.05 in my right tail, what would the area to the left be? There's 0.05 to the right of this value. The area to the left of that would be 0.95, right? Remember, the area under the curve is always 1. So I could type in 0.95 here, but how did you really do that? You just did 1 minus that alpha or that area you wanted in the tail. Like I said, if you want to do that ahead of time, you could have just typed in 0.95 as well, right? And that should hopefully give me the same number of standard deviations, but positive. So once again, you could just use the absolute value function if that's easier. You always look up alpha and then right tail test just that value of positive. Okay. Same kind of idea here. If I have my critical value of about 1.65, rejection region is the area to the right. Where was my test statistic? It was like 0.3, nowhere even close to that rejection region. Same kind of thing with the p-value approach. We said that we failed to reject, right? It led to the same rejection decision. Okay. Any questions on that before we keep going here? I'm a little bit quicker through this stuff with you guys, so have a little more time on the next problem, I think. Want to see any of these cells again, or? All right, so let's go back to that female data worksheet. I'm now going to find the sample mean. So actually, let me write this out just so we have some reference here as we're working through this. So, is it hot here? You know, okay, maybe it's just I'm moving around, but I'm like starting to sweat. So, if we wanted to do confidence intervals for situations where we've got two groups sample means and we're looking for the difference in those sample means, but we wanted to, but we only had sample variances, right? So we worked through a problem Monday where we had the Midwest and South, where we had sample mean enrollments, but we had known given population variances. Here we're going to start out with a situation where we have to calculate those variances. We said it's basically the exact same thing we did on Monday, except instead of known population variances, we use sample variances, and we can no longer use that standard normal distribution. We have to use the student t distribution. Okay, so we've got our confidence interval equation, we've got our test statistical equation in front of us. Once again, that formula sheet's up there under the files tab on Canvas. You're working through homework problems, like having that in front of you, it's probably very useful, right? So I'm going to find the average or the sample mean BMI for my female data. So I'm going to Control Shift Command Shift on that. Hit the down arrow, hit enter. Variance. Well, I've got to find my sample variance, so var.s. And then hopefully we know at this point our sample size. We're just using that count function, right? So sample mean using the average function, sample variance, selecting that variable, var.s, sample size using my count function. Just hopefully things that we've done this quite a bit. So now that I've got these three, oops, if I don't trip and fall, I might be interested in something like, well, look, this BMI variable, I know is not a great it's not a great measure of, I think like my BMI was close to like not being good. So, I mean, it's not a great measure. And so maybe because it's using height and weight, maybe it's like somewhat biased towards females or males, like one way or the other, right? And so maybe I'm thinking there might be some difference between these two, right? Between these two groups, the BMI values might be different. So my second group, I'm going to look at my male BMI, select that, right? Find the sample mean using the average function, var.s, find the sample variance, right? Just select that variable, and then use that count function. So I've now got my sample mean, my sample variance, and my sample size for the males as well, right? But I want to get all this data on one worksheet, okay? So I'm going to go over here, excuse me, and, well, I should have said that before, okay. I'll use an equal sign, then select my female data worksheet, and then select where I calculated that sample mean for that group, right? That female data. And that was my group 2. Okay? Hit enter. Same kind of thing. If I've set it up the same way on my male and female worksheet, then once I reference one of these, I can just copy it down and it updates that cell reference. Okay. So all I've done here is use that average, that var.s, and that count function to find the sample means of both groups, the sample variances, and the sample sizes. Okay. I also kind of use this cross worksheet reference. Once again, you don't have to type this in. If you start with the equal sign and then click on the worksheet, it automatically will throw it in there for you. Okay. Any questions over anything up to this point? So if I'm working with a student t distribution, one other thing that we're going to need that we didn't need with a standard normal is our degrees of freedom. I showed you the equation. It's pretty nasty. I said, I'm not going to make you do it, right? So notice here, I already had it typed in ahead of time, right? There's a lot of parentheses going on here, right? It's very easy to make a mistake, right? And so what I'm going to do, and then once we have it calculated, there's this floor function in Excel, which kind of pushes it down to the next lowest integer, which is what we said, if we have degrees of freedom, it has to be an integer value, okay? So what I did in the Excel assignment, identical to what I just had here. I had the function already typed in. As long as you calculate your sample mean, sample variance, and sample size in the cells that I was like, in this next time, I set this all up pretty nicely. Right? I already got some of the work, kind of the scaffolding kind of done. As long as you calculate your sample variance, sample mean, sample size in these cells, this will automatically give you that degrees of freedom. Okay? I have it set up the exact same way. And it's because, like I said, I understand it's just an exercise in well, I guess maybe there's some value to this, but an exercise in how attentive to detail you can be, right? There's just a lot of parentheses here. Okay. So I've got my degrees of freedom. I'm going to go down here and start to calculate some confidence intervals. So I've got everything I need: sample sizes, sample variances, sample means. I just need to figure out that number of standard deviations where I need to go to get alpha over 2 on each side of my confidence interval, right? And now, instead of a standard normal distribution, I need to use a t distribution. Okay? So I'm going to look this up. Use t.inv. So before we were using norm.s.inv to find our z values. So now we're just going to use t.inv to find our t values. Okay? What area do we want, or what probability do we want in each tail? Alpha divided by 2, comma, we have to tell the t.inv one more thing that we didn't have to tell the standard normal inv, right? Which is, well, what student t distribution am I using? What's the degrees of freedom? Well, we've got this calculated up here, right? So this will give me that t value that gives me alpha over 2 on each side for this specific degrees of freedom. Now, if I copy this down, what's going to be a problem? I want to get the t value for the next confidence levels. Yeah, my degrees of freedom isn't changing. So notice if I don't do anything and I copy this down, I start to get some errors, right? So I need to make sure that, oh yeah, that degrees of freedom, shouldn't be updating, right? It was like updating to blank, but that's why I'm getting errors, right? So make sure that degrees of freedom is frozen. What's another issue that we have? Yeah, the positive and negative are already kind of built into my upper and lower bound equations. So here, I'm just going to take the absolute value, right? Now, if I copy this down, I'm getting some values that look make a little more sense. And I don't know why I didn't do this as upper bound here either. So I've got these 3 t values. I've got everything I need now. Now it's just a matter of using Excel to my calculator to find my upper and lower bound. Now, before we do that, I just want to kind of point something out. These values look really similar, or look really familiar to me. So if I look at these t values, they're really, really close to these z values. But why? My degrees of freedom is 6,000 something. We said as that degrees of freedom gets higher and higher and higher, as our sample sizes get larger, our student t starts to get more and more of an approximation for the standard normal. So at 6,000, we're like getting pretty close, right? But they still are a little different. And if I'm doing this for a company and I'm dealing with things that are like in the millions, or even billions, if I'm talking about some of the revenue, then yeah, being off by 0.01 or 0.001 might translate to a lot of money, right? So it's really nice that even if we have these high degrees of freedom, we can use the student t distribution function in Excel, where that physical table, right? I think it only goes up to 1,000, if I remember right. So we can be a lot more precise here. So, excuse me. The next thing we're going to do is just use Excel to be our calculator, right? We're going to take male minus female BMI. We're then going to subtract to get our lower bound, our margin of error. Well, what's our margin of error? It's the number of standard deviations away we want to go multiplied by what that standard deviation is. So actually, I'm going to do something here for you guys because I think we're going to have enough time. I think this might make a little more sense. So if I want the standard deviation for the difference in my sample means, right, I can use that in my confidence interval equation and my test statistic. So I'm going to calculate that in another cell just to kind of make my life a little bit easier. So that standard deviation of the difference in my sample means is just the square root of each group's sample variance divided by that group's sample size, right? So I'm just going to type that out over here just so I can have this and kind of use one value when I go to calculate my upper and lower bound instead of typing all of this in, okay? So I'm going to go down here. I'm going to take my male sample mean minus my female sample mean, subtract the number of standard deviations away I want to go, multiply by whatever that standard deviation is. Now, one other thing I'll point out here is when I have a really high sample size, we can get a really, really narrow range of values for this confidence, right? So if I think about my sample size is going up, right? What's going to be happening to the standard deviation of the difference in my sample means? It's going to get really, my denominators are getting larger here, small. So then I'm going to be adding and subtracting a really small margin of error. I should get a pretty narrow range of values, right? So I'm going to hit, before I hit enter here, I want to have this lower bound equation. I want to copy it down so I can get different levels of confidence. What's the only thing that I want to change at different levels of confidence? Yep. So that's the only thing that I don't want to freeze. Everything else, I'm going to go in, freeze that. Similar to the last example, I just want to copy and paste, right, this function to get my upper bound. The only thing that's going to change, so I highlight that, copy it, paste it, should get the exact same value. The only thing that changes, instead of subtracting my margin of error, I'm going to add it. Okay. Hit enter, copy this down real quick. I've now got my 3 different confidence intervals pretty quickly. Okay. So if I look at these confidence intervals, first of all, any questions? Does anyone see one of those cells again, or before I keep moving? So if I look at these confidence intervals, especially the first 2, they only include negative values. So one of, if I assume, I changed this for the other class in that rest back. If I assume that the difference is equal to 0, what level should I be rejecting at, and what level should I be failing to reject at if I'm doing a two-cell test? Yeah, 0 is not one of the possible true values for that difference. So if I assume that it's 0, hopefully I should be rejecting, right, at those levels. Now at the 99% level, it just barely crosses over, right? But that still means that 0 could be, at the 99% confidence level, could be one of the true values. So if I assume that it's 0 at the 99% level, hopefully I'll be failing to reject, right? That's kind of how these rejection decisions line up with these confidence interval values. So go down here. I'm going to find my test statistic, all right? So all that's going to be is using Excel to be my calculator. So I go up here, take my male sample mean minus my female sample mean, right? That's that sample difference that I found. Now I'm going to do this because I'm going to show you something. Usually if you have an assumed true difference of 0, you don't have to subtract 0, right? It's not going to change anything. But I want to show you that you don't have to use the assumed true difference of 0 later. So I am going to include this, right? Just subtract 0. So that's my numerator. Well, what's in my denominator? That square root of each group's sample variance. But this represents the standard deviation of the difference in my sample means. I already calculated that up here, right? So this should be all I need to get my test statistic. Right? So I get this test statistic of negative 2.3. So negative approximately negative 2.3. If I want to find the p-value, right, that's going to be the probability I saw something as many standard deviations away from that assumed true difference as what I found, or anything even more extreme. Except, so I can look this area up in Excel, but I'm gonna have one more step. That could be what? Yeah, so didn't really point this out very well, but this is a two-tailed test, right? We're trying to find out if this difference is anything other than zero. We assume the opposite is true, which is that it's exactly equal to zero. So it would have been equally as likely to see something that many standard deviations away on the other side that also now goes against the null, right? Because now two-tailed test, evidence on either side goes against the null. So just like before, we know the t-value, just like when we knew the z-value, and we want to find the area in the tail. So instead of norm.s.dist, whoops, I'm talking and then trying to type, we use t.dist, right? Using that student t-distribution. Well, what's the t-value that I have? It's my test statistic, right? My test statistic represents a t-value. Comma, what's my degrees of freedom? Well, I've got that kind of had that function pre-calculated there. And then comma, we're always going to use the cumulative option here as well. So it's going to look up this t-value. It's going to find this area in the tail. We said we had one more step, which is then multiply it by 2. Okay. This should give me my p-value. Okay. Hit enter. Sure enough, I get kind of about 0.018. So I'm going to go over here. I don't know if we'll have time for the critical values today. I might do like a shortcut to show you it. But we can make these rejection decisions, remember, using that if function, right? So it's kind of a nice, easy way that we don't have to like maybe miss some zeros if we're comparing our p-value to alpha. Remember, that's how we make our rejection decision. So we only reject if that p-value is less than alpha, right? If that holds, or if that's true, we should be rejecting. So put the word reject in that cell. If that doesn't hold, or that's not true, the p-value is actually greater than alpha, then we should fail to reject. So if I copy this down, every rejection decision at different levels, the only thing changing should be the alpha that I compare my p-value to. So I need to make sure that I look at this p-value cell reference. And when I copy this down, I don't want that to change at all. Okay? So I'm going to freeze that p-value cell reference. Hit enter, copy it down. Well, now I can see, consistent with what we said about the confidence interval, right? I can reject this assumed true difference of 0 at a 95% level, but I can't quite reject it, right? I failed to reject it at that 99%. Right? So this is how that kind of decision between, those values in your confidence interval, as long as we're doing a two-tailed test, like I think I said last class, like one-tailed test, there's a little bit of values that you could reject. But for a two-tailed test, comparing to the confidence interval, any value in that range for your confidence interval, if you assume that the difference is any one of those values, you should be failing to reject, that hypothesis test. Right? So 0 is not one of the values in that range. So if we assume that it's 0, well, then we should be rejecting it. Right? Any questions there? You want to see a cell again before we keep moving here? A couple more things I want to show you before we get out of here today. Well, we'll kind of use a shortcut for critical values. So this is not, I'll show you a shortcut and then I'll show you the right way to do it. If I've got a two-tailed test, what's true about my critical values? Or sorry, I already said it. I don't have just one critical value, right? If there's two-tailed tests, we said we have what? Critical values, right? I've got the same number of standard deviations, but one's positive, one's negative, right? Because evidence on either side goes against the null. So it's the cutoff value that gives me alpha total in my tails, or alpha over 2 in each tail. So what's something that we've already done that we could probably reuse? What did we do for confidence intervals? We literally found the t-value that would give us alpha over 2 in each tail. So if you're building confidence intervals, essentially those values that you find would be your critical values for a two-tailed test. Okay? Now, if you didn't have a two-tailed test, it's a little bit different. But really all we're doing there is, well, what's the area that I want in the tail? Alpha divided by 2, comma, what's my degrees of freedom? Go up here, select that. We'll go back down so you can see the reference. Sure enough, I get the exact same value. Now, one thing that I'm going to insert a column here. One thing that you'll need to do if you are doing this in Excel for a two-tailed test, you need to indicate somehow when, like, this is probably the best way to do it. So, whoops, sorry. That you have this negative critical value, but you also have that same value, critical value, but positive. So taking the absolute value is kind of a nice, easy way to do that. Now you can see, or sorry, we have to do one thing. If I copy this down, I need my degrees of freedom to never change. So I'll freeze that cell reference. Now, when I copy this down, I should get my pairs of critical values, and they're exactly the same as what I was using for that composite. If it's a two-tailed test, right? So for a two-tailed test, I want half of alpha in each tail. Okay. So I'll kind of go back here. Any questions on that before we keep moving? Okay. All right, so I'll show you a couple other shortcuts. So when we looked up that area in the tail to find our p-value, we use that t.dist function. There is a t.dist.2t, right? So I could tell it my test statistic, comma, tell it my degrees of freedom, and it will basically look up what that area in the tail was and multiply it by 2 for me. The reason why I don't typically use this, and what I don't like suggest using this method, is for whatever reason, the way they have this program, it only accepts positive test statistics. So if I hit enter, it gives me like this error. Well, that's okay, because if I think about what I was doing with that p-value approach, I had this test statistic of negative 2.33. I wanted this area in the left tail and then multiply it by 2. Well, if I just used positive 2.3 and it found the area to the right and multiplied it by 2, that'd be the same thing, right? So for whatever reason, they have it so that it always wants to look at the right tail. So if I took the absolute value of my test statistic, right, then it would give me the area to the right of positive 2.3, which would be the same as the area to the left of negative 2.3. And as a two-tailed test, it multiplies it by 2 for me. I get the exact same value, right? Like I said, this is just kind of a headache for me because I get sometimes forget, oh yeah, it doesn't take negative values. So I got to look at it, I'm like, why isn't it working? It's for whatever reason, it only takes positive values. We also have an even better shortcut, which I will ask you to use. So on the Excel, I explicitly say for the first part of each problem, do not use this built-in t.test. I then at the end of that problem will say, now show me what you would do if you use the t.test, right? So you're kind of using the method that I just showed you, right? Finding your test statistic, looking up your p-value, right? Calculating your sample mean, sample size, sample variances to calculate that test statistic. What this t.test function will do is it does all that work behind the scenes. So all I have to do is select my 2 samples. So here I equals t.test. I'm then going to scroll up and select my male BMI variable, right? So I just select that entire variable. It's a big data set, kind of a pain. So I scroll back up. I just want to show you. Oh my gosh, come on. It put that reference in there for me. Now on the Excel, I've got the data on the same sheet. So you don't have to worry too much about this next thing I'm going to show you. Comma, you should just then select your second group. Now, my second group here is that female data. It's on a different worksheet. So I'm going to have to go over here. Notice it puts that worksheet reference in for me, and then select my female BMI, right? Now, a problem is if I select, try to go back to the data, notice, change that. I didn't want that. So go back over here. Okay, it's got the female data worksheet on there. Before I go back to my other worksheet, I need to put this comma. Now, when I go back to this other worksheet, it says, okay, now I'm on the male worksheet. Well, we're not actually going to reference anything here, so it automatically puts that in. We're just going to get rid of that. Okay? Like I said, on your Excel, I put the two kind of samples or the two variables on the same worksheet, so you don't have to worry about that for the problem where you can use that T-dot test. So we've got our, oh, this somehow, why is this not right? Hold on. So I got too busy explaining this to you. Okay, so I'm going to select my first comma, go over here and select my female BMI, comma, like back here. I can scroll up so that you guys can see what I'm doing. Maybe. Wait, where is this? Oh. There we go. So I've got my male data, my female data. The second or the third thing I'm going to tell it is how many tails are in my test. Well, I've got a two-tail test. And then comma, it's the type of test that I'm doing. So it gives me kind of these references. I will say this, and someone will still try to use it on the homework. You will never use option 2 in this class when we're using T-dot test. You will never use option 2. Right? We're either going to use this T-dot test to do matched pairs, or when we're comparing two sample means with different variances, which is like most often the case. Right? So we're going to choose this type 3. We've got two samples with different variances, right? And it kind of gives you that prompt, like I said, to kind of let you know. 1, if you're doing a matched pairs example. 3, if you've got two sample means and you're looking at the difference. So what this T-dot test function does is behind the scenes, it calculates our sample means, sample variances, sample sizes, throws them all into that test statistic equation, looks that test statistic equation up, finds the area to the left or the right of it, depending on if it's a positive or negative test statistic. It's a two-tailed test, and then multiplies it by 2 and spits back out at you the p-value. So it saves us a lot of time, right? So if I hit enter here, I get the exact same value, right? So I'll save myself a lot of time, also just like a lot of space in the Excel workbook. But there is a reason why we might not want to use that T-dot test function. So the reason why I'm showing you how to do it step by step, even though there's this kind of nice shortcut here, right? Is if I ever want to use, and like I said, I'm kind of simplifying these a little bit for this class, I'm always giving you an assumed true difference of 0. So here, this would be like our male and female BMI is different, right? Well, I could say our male and female BMI is different by more than, I don't know, negative 0.3. Is that difference greater than negative 0.3? If I hit enter, my test statistic, my p-values, my rejection decisions all update for this new assumed true difference. But notice my T-dot test doesn't. There's nowhere you can tell that T-dot test the assumed true difference. It can only do hypothesis tests with an assumed true difference of 0. Now that's still really useful because like a lot of the time that's the assumed true difference we want. But anytime we want to know is that difference greater than a certain value, I have to break this down kind of step by step. Okay. Any questions over anything there? You want to see a cell again, or I think if there's anything else I want to say. Oh, I'll say one more thing and I'll let you guys get out of here. All right. I will say this, and someone will not listen to me and still do this. When you're building confidence intervals, yes, there is a confidence dot norm and a confidence dot d equation. It's not completely straightforward how to do it with one population. It's even more confusing, I think, and more complicated to use it for two population examples. So I showed you how to do it the way I did because I think it's an easier way, right? And because I think it's less likely you'll make a mistake. I guess technically you could use these, and if you use them correct, I'll be okay with it. But why try to learn this entirely new method when I've shown you the way, method in class that will take just as much time as if you were using confidence at norm, confidence at T, and it's a lot less likely you'll make mistakes, right? People that tried to use this on the last Excel, nobody used it correctly, right? So I showed you how to work through these examples in class today because that's how I want you to try to work through them. That's the way I think is the easiest way to work through them for your Excel, Excel assignment. Okay. So we'll do matched pairs, a matched pair example in Excel on Monday. we'll then transition to the last topic, which is linear regression. Okay? Questions from you before I let you guys get out of here? All right. Have a fun, safe weekend. I'll see you guys on Monday.